Hello, everyone. Welcome back. Linux Audio Conference 2025. We're starting the next session, session number 4, short one, only 2 papers. The first one is presented by Gizo Grimm, researcher in audio interaction and hearing aids. And the title of the paper is Enhancing Interactive Communication with the Ovi Box. Take it away.
Yeah, thanks a lot. Also, thanks all of you for organizing this conference and for being here. So it's a great pleasure to be here again. And so it's about the Ovi Box, about interactive communication. So you probably all know these telepresence tools, and we all know about low latency. But why do we need low latency in our research fields? So it's, if you would like to go for a natural and effective communication, so we really would like to have an interactive and smooth conversation over the internet. And also, if you have musical interaction, we really would like to go for maintaining rhythm. So Hendrik mentioned that he's mostly doing droning stuff, then maybe low latency is not so crucial. But if you're doing rhythmic interaction, you really need low latency. And also in speech communication, but also in musical communication, we would like to have some kind of sense of connection and engagement in this conversation. So really feel the other members, like the real presence of them. And we all know that the traditional tools like what we have, like Zoom or so, and even telephone, they have limitations. Mostly it's a latency. So in a typical phone application, you have delays of around 150 milliseconds or longer. In Zoom, you have something like 500 milliseconds, or if you're going for Jitsi, you can have even 700 milliseconds of latency between the input and output. And also in most of these tools, we have a huge signal degradation due to an echo cancelling algorithm. So for music, it's very poor, because if you have autocorrected signals, they degrade. Also, we have lots of noise reduction, which it blocks all these like breathing sounds and the side sounds, which you also need in music. And well, also most of these tools don't really provide spatial reproduction, which is, I think it's a pity, because it would be so easy to add to all these conferencing tools and would help a lot really in perceiving the sounds and knowing who's next. And well, there are some low latency network tools around. So I'm mostly looking into tools which can provide end-to-end latencies below 30 milliseconds, which are mostly Raspberry Pi based. So we all know Jack Trip. I mean, it was mentioned several times at this conference. There's also SoundJack, which is a closed source project. And so I developed, at the pandemic, the Ovi Box, which is completely fully open source. Actually, I looked a lot into Jack Trip because I like it. Well, I liked it, but I still like it. But I needed some features, and sometimes it's easier to do your own stuff than just digging into some other stuff. So that's why I developed my own tool. It's fully open source, but it's also non-commercial, so there's no commercial trap or so behind. And also all these web services, it's not only the source code of the application, but also all the web services and everything is also published and available. So what is the Ovi Box system? So it offers some kind of, it's a session management system, and it's via web server. So it's mostly, if you're running Raspberry Pi, you want to have a headless device. There's tons of documentation, so it's mostly for the non-technical users, so how to plug it and how to, I mean, you know, non-technical users can do all of, so I have these sound cards and they can do all the stuff, plug everything wherever it's possible, so doing the wrong way. So that's why you need lots of documentation, even how to connect a USB cable. And some really focus on addressing also non-nerds in the music domain. And well, I mean, I think if you're all nerds, so you're not the target audience, probably, or the only target audience of this tool. So we have hardware-based solutions, but also software-based, so desktop apps, which is, for some people, it's easier. And well, we have the desktop app on Linux. I have to say, also on Mac, it runs very smoothly, and I tried to port it to Windows, but since I'm not really a Windows user and I try to avoid it as much as possible, I don't really know if it's working or not. So we do head-track binder rendering, and we have kind of like source movement and remote source movement as well. So if you're playing a trumpet, for example, you can have all these directional sounds transmitting your trumpet source movement, for example, to the remote listeners to get a sense of movement which they're doing in low delay real time. And we can reach rather low delays. So in a local network, with, like for example, for monitoring, we also use it. Then we can go down to 7 milliseconds or below, depending on the hardware as well. And in a typical setup, we reach something like 30 milliseconds, so fiber optical connection within Europe, for example, or within one continent. And if we are using mobile phones, it's more like 50 to 60 milliseconds, which is on the edge for rhythmic interaction. And well, I originally developed it for musical interaction, so for my ensemble Orlando Wilds. But I'm now using it mostly in academia for research. I mean, I'm still using it for my ensemble, and many other ensembles are using it, especially well, it's very easy to just plug and have a rehearsal. And since we are here, I just would like to have one comment and maybe a question, because many people like this sound device because it's very cheap and easy to use. On the Raspberry Pi with the old kernel, like with the kernel 5 version, it works very smoothly, the sound device, but with the 6 kernel 6, it has lots of dropouts, and I don't know if anyone knows about this and how to fix it. So with the Raspberry Pi, with the Pi 5, for example, I cannot really run this device. I don't know. And there were lots of changes in the standard USB sound driver in the kernel, but I don't know how this affected this device, which is a pity. So I'm still a bit stuck with the old kernels. How does it work? So we have a client-server architecture, and so we have a configuration server, which is openly accessible, so it's a user interface. Then we have some kind of session server, which is some kind of management of connecting devices, exchanging IP addresses and ports. And also it's some kind of firewall tunneling. And then we have all the devices. It supports different network topologies, like it's this selective forwarding unit. So it's a central server, that's one mode. It's saving data, but it reaches slightly higher latencies, typically. And we also have a peer-to-peer mode, and it can be configured easily and switch between those. It supports mixed modes, so it can combine both. And well, none of my software tools would exist without fonts, so that's why we are using, so it's all built around Zeta and JBridge, which is a great tool. Mostly, I think originally was more developed for local transmission, but I just used it and extended it, put all these network forwarding into it, and I'm still using this as a core for doing the jitter compensation and also all the delay management. And I'm using another toolbox which I wrote. It's a Tasca toolbox for spatialization of sounds, which is doing low delay spatialization. And so this creates binary head-tracked rendering. It can also be extended for loudspeaker reproduction, so you can easily plug in a 5.1 system or any kind of Ambisonics device for reproduction. And well, we have some new features. Well, I don't want to talk too much about these new features. It's all in the paper. So one is it's easy to embed in any arbitrary UDP messages, like for example OSC messages, and using the same system. So if I create a session on the web interface, I can share my data between all these clients. So I just plug any USB, or I just use any USB stream in this local network, and I'm forwarding it to the other ones, and then I can still use it to control devices. I'm using it a lot for controlling light, for example. If you have a music session, like on stage, having hybrid concert performances, for example, then you can have one client having their own lights, own lamps, and still having the same effects remotely and locally. But we are also using it for motion data transmission or even EEG data transmission. I will come to that later. And we also can transmit additional timestamps, which is also useful. And the other major addition now, which I added recently, was the total encryption of the audio, so the end-to-end encryption. And it's using public data key exchange, so it's a key pair encryption, using Lipsodium, which makes it very easy to add encryption to the data streams. I also have to say, so my servers are publicly available, so in the last year, there were many attacks and attempts to hack it, and so that's also another reason why I added it, and also in our academic research, we really have to stick to the data protection rules, and that's why we needed it. And it works in both operating modes, so both the peer-to-peer mode and the selective forwarding unit mode. And with the encryption, I have to say it's a tiny bit of overhead, because especially if you are using very small block sizes, then of course for adding the encryption, we need additional data. So we have something like at a typical block size of 2 milliseconds, we have 20% overhead. But in the audio thread, there's no measurable overhead for the computational flow. I mean, of course, there's some computational overhead in the non-audio threads, but you cannot really measure it on a Raspberry Pi. And so that's why it makes it very useful. So much about the technical details of it. And now I would like to present some applications. So one is like a typical application, or our first use actually in the pandemic and this concept was streamed in July 2020. So it was after a couple of months after I started developing the whole tool. So we had a live concert, or we had a series of live concerts with multiple musicians. So in this case, 6 musicians in 5 different locations in different cities, so really not connected physically. And again, we were using, we had our own interaction, but we also were using the Tasker tool for spatializing and simulating like a concert hall for the stream. So we had our own monitoring system with a low latency, and we also had the stream out system, the rendering system for the rest. We were using Blender for creating some visuals. I mean, usually the audience would like to see some visuals. So we just had some kind of interactive 360-degree video. And, well, putting a lot of load on the local network connection, because also I'm based in Germany and the internet in Germany is very poor. So I just had to order the fastest fiber optics which I could get at the time. And still it was on the edge. And yeah, so we had some tools. You can, if you like, you can look at the stream, but it's still on the net. And I would like to briefly display it a bit. The next slide will be a bit messy, but I will try to demonstrate how the signal flow was done. So we have the 6 musicians here. You see from the left to the right. And 2 of them had a very poor internet connection, so one was even connected only via mobile network. So this means if you really go for lowest latencies, you have some dropouts or many dropouts, depending on the connection. And so for those with poor internet, we needed to use this selective forwarding unit mode, which means all the audio goes via a central server. All the other ones were using, so not all, but most of them were using like the peer-to-peer mode. Also, there was one special case, which I wrote called the proxy mode. So this device also can be configured to have, if you are in the same local network, so one device can be configured to be a proxy. You can also, again, save data, and then this local device is forwarding the data to all the other ones in the same local networks. So this was the case because 2 musicians were in the same house. And then we had this rendering on this, well, I don't know, I can try to show it here. Maybe you can see the mouse cursor. You have an additional OV box here for the rendering. And this was containing a slightly larger jitter buffer for the jitter compensation, because we don't want to have all the dropouts on the audio stream, and for streaming out to YouTube, you have a delay of 20 seconds or so. So all this jitter buffering doesn't really make any difference. And so we had our, I don't know, it was something like 50 milliseconds jitter buffer. We also had cameras using, I don't know if it was Digi or Video.Ninja. And in these video streams, you have something like a 400 milliseconds delay. So that's why we delayed our audio again by something like 400 milliseconds to have more or less like a sync between the video and the audio. But this was done only for the stream. The musicians didn't see any video, because our experience is if you see the videos of the others and trying to play rhythmically together, it's completely a mess, because you cannot, it's far too late. Also, I mean, also perceptually, it's something like it's decomposing, because our brain is quite calibrated to have the video signal always earlier than the audio signal, because the speed of light is faster than the speed of sound. But this means if the audio signal comes earlier than the video signal, our brains doesn't really combine those 2 streams. Well, and then technically we all sent to OBS. I mean, it's a quite common approach, and then sent it to YouTube. Unfortunately, YouTube 360-degree video streaming, the live streaming version, doesn't support ambisonics. So the audio was just stereo audio. It was not interactively rendered as an ambisonic stream. So this is one of these music applications. We also did some kind of mixed hybrid concerts, and we are using it a lot for rehearsals. So our research applications, which is more like an academic approach, is as in the field of hearing research. So I'm working on hearing aids, developing hearing aids and interaction of hearing devices. How can we control hearing devices and how can we evaluate hearing devices? And for the evaluation, we are typically working in a lab. So I mean, we're doing experiments. So let's say a hearing impaired person comes with devices and we're doing measurements, how good do these devices perform. And typically we are on the left and we have like, I don't know, it's like a speech test. People are responding to a test, sitting in the lab, having one loudspeaker in the front. So it's only one stream, one signal. And you can have very sensitive tests in the range. But then if you look at the real life is more on the right side. So we go to a party and having problems discussing or understanding our neighbors and having a conversation there. And this is a completely different field. So here we don't have the sensitive measures, but we have completely natural behavior. For example, maybe in the field, in the party, we are dancing or so, we have lots of movement behavior. And so we would like to go more to this natural behavior. And so what we try to do is we try to bridge this gap. So we add virtual acoustics, we have audiovisual content, we have controlled interactions, so some paradigms which are not really speech tests, but more interactive. But then we go also for free conversation, so free interactive conversation. And here, this is something where we use the OV box again, because we would like to control parameters. So I will skip most of this, but if you have face-to-face conversation, we have, well, it's a verbal and non-verbal conversation. So we would like to investigate and understand all these parameters of conversations, and this conversation contains rapid switching. It also contains a lot of prediction, because, for example, we need something like 600 milliseconds to form a sentence, and so our brain needs some time. But usually the gap between the end of another speaker and my start of the new sentence is much less than that, so which means I had to predict the end of the previous sentence. And that's something which we really have to take into account. This is also one of the reasons why we really need, if you would like to do research in this field, we really need to have extremely low latency to have natural conversation behavior. And there are some measures which we are trying to look at. So, I mean, it's mostly speech activity based. So if you have, for example, turns, if you have an interactive conversation, we have some timing differences between the end of a sentence and the beginning of the next one. We also have some kind of situation-dependent features of the speech, which we can analyze for controlling or for evaluating devices. But we are also looking a lot into gaze behavior, into saccades, so fixation points. Where do we look at? And how often do we look at? And what's really interesting is the interpersonal synchronization. So if we have conversation, we are mirroring some behaviors. For example, eye blinks are mirrored at a lot. Nodding behavior is really interesting. So, I mean, there's all this back channel information. Some of you nod, you are not nodding and or just sleeping away or so. All this information which you are providing back to me is something which you typically can analyze and see how well this conversation is going on. Well, and this is what we are doing in our research. So we would like to use telepresence and combine it with virtual reality to have free conversation, but still have to be able to disentangle all these factors which are influencing it. And, for example, to control some of these behaviors. And for that, we need to have like a very, I mean, for the temporal analysis, for example, we need really low delays. For analysis of voice features, we need highest quality. And for analysis of gestures, for example, we need transmission of like non-verbal features as well. Also, we would like to have facial expressions. We are not there yet. And, well, as you can see, all of these, or most of these features are covered by the tools which I presented, which I developed. So that's, let's say, it's kind of optimal tool for it. And, well, very quickly, so one research we did, it was a master thesis in our lab, was can do avatars. So does head movement, for example, influence the way we perceive speech and how well we perform in a conversation? So it's head movements of avatars, so we can have some kind of situation where we have, so the test participant sitting in a lab with a big screen. Yeah, this is the test participant. We have a visual representation of an avatar here. I'll show a picture of it in a moment. And we have remote interlocutors who are having a triadic conversation with those. And now we can look at all these features and we can control features of the avatars. So in real, it looked like this. So we had it's in some kind of cave-like system we have. And we have avatars controlled in low delay real time by these remote listeners. And what we see is, well, I mean, you can read all the papers if you like, but the main take-home message is we can control it, we can see effects of head movement, for example. So we were able to disentangle some of these features of conversation. And, well, I mostly skip this second because I'm running out of time, but so we also did some kind of experiments with EEG hyperscanning. And so hyperscanning means that we are recording the EEGs, so the brain signals of several persons at the same time in a conversation and doing it really in a synchronized way and doing it in several tasks. So this is a typical setup. We have like remote participants here in different places. We have central data logging, and we are also sending clock signals of synchronized clocks to be able to analyze this data later on and having like a real timestamp and good time basis. And here just some examples. It's just, I mean, I won't go into the details, but what you can see is some reactions, and it's just a demonstration. It works. And we are going to do this also with other technologies like EEG, but also MRT and huge medical data labs. So, well, where to go next? And, well, of course, we would like to do many more scientific work on this field. And the main message, and I have to say, I was really impressed by the talk about all these smell tests and the software development and architecture. So what we try to do is we would like to keep the OVBox system up and running. I'm in good position that I have a permanent position at university, and I'm the main developer, so I have the funding for supporting it and keeping it up to date. We need to do lots of bug fixes, of course, and maintain the CI and CD pipeline. Yeah, and if you are interested in a very hot demo, you can come to the coffee break in the afternoon at 3:30, and I will show you the system. And my student in Oldenburg, back in Oldenburg, will talk to you and showing head movements and all this stuff in real time. Thank you.
Thank you, Gizo. Do you have any questions? Questions from the audience? Yes, up there. Maybe we can pass the mic.
Thank you for your talk. Is it possible to set up a server? Because I've just skimmed the website and I haven't found anything about it.
Yeah, I mean, of course, it's possible to set up a server. It's the source code is public. The documentation is a bit missing. It's for setting up a server. Well, the documentation is mainly for the main users, but I should set up a server documentation as well. And it's possible to set up both. So it's both the relay servers, which is doing the audio transmission stuff, and also the web interface. But I have to say the web interface is very poorly programmed in PHP, JavaScript, so I'm not a web developer. So.
We have time for another question. No question? Yes, again, up there. There we go.
You were talking about having issues with the 6 kernel.
Yeah.
I had the same issues when I switched from the 5 version to the 6 version with USB interfaces. Did you try enabling implicit feedback with the Focusrite device? Because maybe that could help.
And sorry, in what sense do you mean explicit feedback?
Implicit feedback, yeah. Don't ask me what it does exactly, but enabling it as a kernel option takes away all the dropouts, because I had the same dropouts.
Okay, thank you.
That you were talking about. You were talking about a demo with the coffee break later on, and I could show you, because I'm almost sure that when we hook up the Focusrite to, say, my laptop or any other laptop with a new kernel, and you run it without the kernel option, it will definitely show dropouts when you use it at a lower latency. And as soon as you enable the kernel option, maybe they're gone. So we could check later on, maybe.
Yeah, thank you.
Yeah?
Great,
Okay.
yeah. So that's why we are here. I mean, all the experts are in the same room.
All right. Let's thank again Gizo.
Thank you.
So while we're setting up, let me introduce the next presentation and next presenter. The presenter is Maxim Popov, recently graduated and presenting today the continuation of his thesis project. The title is Polyphonic, FPGA-based hardware for spatial audio. All
Thank
yours.
you. So thank you everyone for being here. So yeah, my name is Maxim Popov, and I will present you my project, which is called Polyphonic. So what is Polyphonic? So first, it's a project born from the CIFALA project that you may have heard of, which is a research initiative led by the Emerald team, so in Lyon. And is basically what I did during my PhD that I graduated in December. So right now I am trying to find some industrial application for what I did during my thesis. And this is the project, the CIFALA project and everything around it. I will present it now. But yeah, I try to find some application for it. So the idea behind Polyphonic is to simplify the design of ultra-low latency multi-channel audio system by making FPGA technology accessible. So to give you an order of what is possible with this system, you can imagine a system with hundreds of channels that can be processed at a very, very low latency. So we are talking around, we can go up to 11 microseconds from analog input to analog output. So yeah, around a factor of 100 if you compare to industrial systems that are usually at the milliseconds, and for another 10 from the state-of-the-art. And so the idea is to unlock new possibility, new capabilities for many audio domain, such as active noise cancellation, 3D audio specialization, and so on. So what exactly is Polyphonic? So it's two main components. First, it's a dedicated software environment that allow you to program an FPGA way more easily than what is possible right now for audio. And a development board that allow you to interface with existing audio system. Because right now, even if you are able to program an audio DSP on an FPGA, there is no audio development board. So you will need to do the whole audio interface with ADC and DAC, etc. And we have the possibility to implement a custom Linux distribution on a CPU that work with the FPGA on the board. And you can profit from a lot of Linux drivers such as OSC, MIDI, and so on. So the presentation will focus on the project and what I did in my thesis. So first, I will try to explain you very simply how an FPGA works and what it is. Next, we'll see the challenges of using FPGA for audio and why they are not more used. And then we will see more in details how the CIFALA toolchain work and how the hardware board are designed. So first, we'll see what is an FPGA and how can we use them for real-time audio DSP. So very briefly, if you want to program a real-time embedded audio system right now, you have many solutions. So this list is not exhaustive at all. But if you try to have the lowest latency possible, you can use a CPU. So basically, I suppose you will use Bella or Elcodio. Those are CPU based on Linux Xenomai. They can offer sub-millisecond latency latency but because they work with an OS, you will still have to buffer your sample, so you cannot go way lower than 1 millisecond latency latency. You can use a microcontroller, so same idea, you can have 1 millisecond latency application, but they have very limited computational power, especially if you want to have dozens of channels. You can use a GPU with very promising academical application right now, but it's still very hard to use. Or you can use an FPGA. So an FPGA is highly adapted to high polarization and low latency latency latency. So first, you don't have an OS on the FPGA, so you can have a sample per sample processing, so no buffering. You can have very high sampling rates, so both give you a very, very low latency. And the FPGA chip usually have lots of GPIO, so a physical pin where you can connect, that allow you to have a lot of audio channels. So in fact, they're already used in some audio products. You can see here, for example, but there is many others. So you have the Novation Summit keyboard. They're used to implement a high frequency oscillator in the interrupt audio interface. The holoplot system, it's a 96 speaker matrix where they implement beamforming algorithm, or in some digital mixer, sometimes there is like many FPGA in one mixer. So they're already used in audio products, but not so much. So why we don't use FPGA more in audio? Well, because they are very, very hard to program, because they are very low level, and so you need to have some microelectronic knowledge. So what is an FPGA exactly, and why is it so hard to program? So you have here an FPGA, so it's just an integrated circuit. So to be exact, here it's a system on chip, but it's an integrated circuit that you will reconfigure. So you don't program an FPGA, you reconfigure it, because it's hardware blocks inside it, and you reconfigure it using hardware description languages, such as VHDL or Verilog. So the basic element of an FPGA is something called a configurable logic block, which is made out of a lookup table and a flip-flop register. So the LUT do the logic function, and with the flip-flop you have the scheduling. You have many of them. You have some memory block called BRAM, some DSP block. Nothing to do with audio DSP, it's a hardware or mathematical function. And a lot of interconnection. And by configuring everything, you can implement any function that you want. So the very important notion here is that you have a limited number of resources. The four main ones are the four I present here, so the LUT, flip-flop, BRAM, and DSP. And if you try to implement a program that saturates one of them, so you don't have enough on the FPGA you want to use, you cannot implement your program. It's not like in the CPU where theoretically, if you have enough, you can afford enough processing time, you can have very complex program. Here, if you don't have enough resources, you cannot implement it. So you need to save resources as much as possible. So usually to program this, we use, again, hardware description language. They describe the structure and behavior of the circuits. So you design the circuit, and the synthesis tool will implement it on your board. It's very hard to use. You have to know how microelectronics work, and this is why basically FPGA are very hard to use. For many years now, we have something called high-level synthesis, which is a design methodology that allows you to program an FPGA using software-based languages such as C, C++. So yeah, we can program them using C++, which seems great, but it's not so easy because you are trying to use a sequential language to program a parallel hardware circuit. So it's worked, but you need to give a lot of guideline to the high-level synthesis in order to know what you are implementing, how you are implementing your circuits. I will show you an example of this. Here you have a very simple example of multiply and accumulate that can be used in a FIR filter. So you just try to do 10 times I times I, and you put it in an accumulator. The question is, if you give this to the high-level synthesis, what kind of circuit will be implemented? Do you have a sequential circuit, so you only implement one multiplier, one adder, and you just reuse this 10 times? So it's use a lot of latency, but it saves a lot of resources. Or the opposite, you parallelize everything, you implement 10 multiplier, it's very fast, but you use a lot of resources. None of them is better than the other. It depends on what you want to do. The question is, how do you give the information to the high-level synthesis? So you need to give a lot of information in order to know which implementation you have. So it's a problem because it's some hardware knowledge that you not especially have. So this is the first problem, but that's not all. So we don't only use an FPGA, we use a system on chip, which is an FPGA plus a CPU plus some other drivers. So once you have your FPGA implementation, you also need to interface the CPU and the FPGA. Everything has to be done by hand. It's not like when you use a TINZ and everything is already done for you. Here you have to interface everything. You have to interface with external DDR memory. You have to balance computation between FPGA and CPU, because again, you need to save FPGA resources. So if you can do some computation on the CPU, you want to do them. So you have to know which computation in your program can be done on the CPU. You have to interface with external audio codec. What I call codec is not a software codec, it's just an ADC and a DAC. So you have to interface with external audio domain. You have to deal with clocking issue that you will have, I can guarantee you that. You have to, most of the time, you write some part of the program with HDL, implying the use of fixed point. And as I showed you before, you have to think as hardware circuits. And finally, you probably want to implement a Linux on your CPU. Some example exists that are already pre-built, but most of the time you have to build your own Linux tailored to the needs of your DSP. So you have to do all of that. This is what programming an FPGA is, and this is mainly why we don't use them more. This is too much work. So what Polyphonic want to do is to simplify the whole process. Basically, we want you to only write a program in a high-level programming language, and you don't care what happened, and you just have something that works on your system on chip, so on your FPGA and CPU, that is efficiently implemented and that makes sounds. So you don't need to know anything about hardware design. We want to do this keeping the lowest latency possible. We want something scalable. If you want to write a program that needs 100 outputs, we don't want you to modify the whole implementation. Everything should be automatized. And again, we want to do this in an optimized way. So how does it work exactly? So now I will present Cifala. So again, Cifala is the research project and is the software part. So the whole toolchain that take as an input a high-level programming language and implement everything on an FPGA. So yeah, you have here the idea. So we use FOST, the FOST programming language. So it's, for those who don't know what is FOST, it's a functional audio programming language. And we want to just write some DSP in FOST and have something working on the FPGA. And that's all, just with one command line. This is the first idea of this toolchain. So it seems very simple like this. How does it work? So this will be a little bit complex. Try to go slower. So you write your DSP in FOST. So you have one file that just implements your FOST program. You can develop it on the online IDE, and once you have something that suits what you want, you have your program, you input it in our toolchain. So the FOST compiler will generate 3 files. The 2 important ones are the one here. At this stage, we want to separate the computation that can be done on the CPU and the one that can be done on the FPGA. How can we do that automatically? Well, we base this on the sample rate, control rate idea. So when you have a CPU, usually, and you work with some buffers, you will update the control, most of the time, only once for one buffer. So the control rate is way slower than the sample rate. So the critical sample rate computation are kept on the FPGA, and everything that can be done at the control rate is on the CPU, which is less critical. The FOST compiler already knows this information, so it's fairly easy. We modify it a little bit to have two different files. Yeah, we modify it thanks to Jan Orla and Stefan Letz, of course. And so you have your 2 different files. So the gray file here will be implemented on the FPGA. So this time we will using the high-level synthesis. So we made it in a way that the FOST compiler writes the code in order to be fairly efficiently implemented by the high-level synthesis. And so we can generate a hardware IP, so it will be a functional hardware block inside the FPGA. For the CPU part, so you want to have a Linux that controls everything. So we added a custom Linux based on Alpine distribution. We generate a bootable SD card, and we implement it on the CPU. So just to be clear, everything is automatized. Everything depends only on the FOST file you write. and then you don't have anything to do. Then we adapt the audio interface, so depending on the number of input, outputs, sample rates you want, we create the adapted audio interface. We interface the memory and everything between the CPU and the FPGA. And we want now to control this. So this is where the third file is used. So the first compiler can generate a user interface based on your DSP, depending on the controller that you want. So you can have this file running on a host PC, and then you can directly control your application from an host PC. And there is many other way of controlling it because you have a Linux, so you can have all the drivers. So right now we can use a MIDI board over USB. You can use a smartphone and use a HTTP control. You can use Ethernet directly to your host PC, or you can use a hardware board that I developed that communicate with SPI. So again, everything I showed you before is automatized. What you can do is, so it's open source, you download the toolchain on the GitHub, and just, not only the toolchain, I will come back to this later, but once you download all the tools you need, you can just write your first DSP called the Cifala toolchain, and just with one line here, sorry. You wait 20 minutes, it's the problem with FPGA, you have to wait a long time to have the full implementation, and you have your program working. You have some customizable parameter, and yeah, you can have an estimation of the resource usage with some option for not having to wait 20 minutes. This is some of the controller you can use. So yeah, I already talked about it. This hardware board, you have the GUI generated by Faust, or you can use some MIDI controller. Very important, this is what is printed in your terminal once you call the command line. Again, I want you to not especially understand how hardware design works. So if you remember well, you have those 4 resources that are critical. All you can see here is that the 4 resources are less than 100% of the resource usage. That's all I need to know, so this program will run correctly and will fit on the FPGA. If it's more than that, it will not fit. So there is a limitation. It's not so easy. So you can do that, it will work, but it is not very efficient. You can see here 2 implementations of an FIR filter, one in Faust, one in C++ by hand. The C++ one is way more optimized. The reason for that is that the high-level synthesis tool needs a loop structure in order to implement hardware pipelines that are very efficient to reuse hardware and to win a lot of latency. So it needs loop structure. The problem is the Faust compiler, the first thing that Faust do is flatten all the loop in your program to optimize it. So right now we don't have loops in the code generated with Faust, which means we don't have pipeline optimization, and worse, we don't have hands on the trade-off between latency and resource usage. Because as you can see here, the execution in Faust is very quick. We don't need 1.8 microseconds. We have 20 microseconds at 48 kilohertz. So we need to balance, to use less resources maybe and more latency. And to have this trade-off, we need loops. That's why we implement the second version of the compiler, which now can take as input C++. So you can write your own C++ program. You still benefit from all the toolchain, the driver, and everything. But you can program them in C++, which means you can implement more complex program, and then you have the hand on the trade-off between resource usage and latency, and you can have directive and pragma to manually optimize pipeline. So yeah, just quickly on this, you still have to do manually stuff, and I say you don't have. The problem is high-level synthesis have a default behavior that is not adapted to audio program. It's a resource-saving behavior, and for audio, the latency constraint is very, very hard. So we want to use latency, to save latency more than resources. So we need to modify the default behavior of the high-level synthesis. So yeah, you need, if you use C++, you need some hardware knowledge, but we have documented many of them. We have created some API to facilitate the work. Now, yeah, very quickly, I will present the hardware part. So now you can program an FPGA, but you still need to implement hardware and to have multi-channel system. just 3 examples of multi-channel system with a lot and a lot of speaker. I'll go quickly on this. So how do you, what is the maximum speaker you can imagine on a system? So usually you use the I2S protocol, which is the standard to communicate with ADC and DAC, audio ADC, DAC. It's basically 2 wires, so 1 clock and 1 data. And you can have up to 16 channels in 1 data wires. So for each new 16 channel that you want to add, you only need 1 wire, so in other words, 1 GPIO. And here you have the number of GPIO available. For example, in fairly used FPGA, you can have up to 250 GPIO, which could be 4,000 speakers, 4,000 channels connected to one system. It's theoretical, I never tried it. I don't have 4,000 speakers. This is just an example of the first board I developed. This one is, 2 of them are open source on the GitHub. This one is made to be manually handmade. So you just need to find a way to print the PCB, and everything is hand solderable, and yeah, you can. It's for a DIY system. And the one I come here to present to you is, so this one I can show you. The idea is to have something kind of plug and play. It is working with 32 inputs, 32 outputs, up to 182 kilohertz. And you have the FPGA directly implemented, so you can program it with Cifala, and you will directly have sounds. And for now, the cost of production only is fairly low compared to existing system. Yeah, I'm done. Just what can you do right now? You can download the Cifala toolchain. The only small problem is that you also need to download the manufacturer software, which is 200 gigabytes, and you need to have Linux. There is many applications working in Faust right now, but we want to have more. Cifala is already used in some university. I think Menus and the presentation you saw before used them. I'm not sure. Yeah, still the case. Yeah. And yeah, there is some C++ application with Central Lyon and some other company right now. But what I need is other applications. So if you have any idea, if you want to try to use this, please come talk to me. If you have any idea of company that could be interested, also I can take this. So yeah, thank you very much. You have my contact here. Yeah, thank you.
Thank you. Thank you, Maxine. We have time for questions. Yes, oh, so many. So we can actually move the microphone side by side. Who was the first one? Here.
So how far, so I have my own DIY 8 and multi-channel setups, and I always need equalization for the speakers. How far away from using that in a DIY context would you think it is? I mean, like the DIY board that you presented, could that be used, or is that something that would be prohibitive in cost for a simple home system?
You mean to use it as a, like I just gave it to someone and you use it as a DIY project, right?
Yes, something like that.
So I would say it will depend. If you program your DSP in Faust, that helps a lot. It is usable as it. It will depend a lot of what library you use in Faust. Not all of them are usable, and yeah, I didn't have time to talk about it, but depending on the implementation you use, for example, if you want to just generate a sine wave, if you use a wavetable, you will have a lot of memory access, which is very bad for an FPGA. If you use a resonant filter, it's very efficient on an FPGA. And it's probably the same for your program, but you just have to know which one to use. And for now, this is not very well documented. That's why also I need a lot of application to know which one are usable or not. But if you have the energy to install the manufacturer tools, it is working fairly well. But yeah, it will definitely depend on what kind of program you want to implement.
Thanks.
A mixer is pretty good, very easy to implement.
Okay, cool. Thanks.
Hi. Thank you very much for that great presentation. I saw that you exclusively use Xilinx tools at the moment, so yeah. I guess that would be one limitation at the moment. Is that right?
Yeah, only Xilinx tools. We are looking for Lattice open source tools, but that just means rewrite everything. So yeah, for now, Xilinx only. We have to do a choice. It was Xilinx and not Altera, but yeah.
Okay, great. Thank you.
Yeah, quick follow-up on that. Are all the Xilinx tools for free available right now, or do you need to pay for them?
No, so the license is free.
Okay.
So you have to pay the FPGA, of course. But
And can your compiler detect if the Faust algorithm is too complex to be compiled on an FPGA? Does it bail out and say that too many gates would be required?
yeah, so there is an option in the command line that allows you not to wait for the full implementation, which is, again, 20 minutes. You will see that your bar graph exceeds 100%. So again, the problem is that with Faust, you cannot do much. If you program in C++, you can tune your program in order to have a more efficient implementation. But yeah, so you need to install the Xilinx tool to know that. The Faust program cannot tell you that.
Other questions? Yes.
Just a correction for this question. It's not free. It's free for some devices.
Yeah,
So,
it's free for this one.
For Spartan 7, for some small system on chips, but for automotive devices and so on, you need to pay, and really, really much.
Yeah, the license is very expensive, but for the one we use, it's free, so that's why, yeah.
Other questions there?
Yeah, concerning the limitation Maxime was saying about the current Faust version, Yann Orlare is working on some interesting new feature added to the compiler. The idea basically is rebuild structure inside the signal part inside the Faust compiler so that we could, in some sense, rebuild the loop that are needed when we deploy on FPGA. And so basically, Yann has already a system to detect automatically FEAR and EER kind of filters and get the coefficient and then possibly add a code generation step, generate the code in a new way. So this is not yet deployed, but at some point we hope that this kind of approach could solve part of the problem described by Maxime.
Yeah.
We have time for another question or follow-up? I do have a question. It seems that we don't have to worry about round-trip latency, audio latency, right? We don't need buffering. We have very high sample rates. Amazing.
Yeah.
What about control rate? Is there any improvement in control rate compared to typical CPU approaches and embedded audio Linux boards?
So for now, it's best effort strategy for the control rate. So you can use Linux as I presented, but there's also a bare metal implementation if you want to be as fast as possible. And then it's best effort strategy. So it depends on what your controller are, but basically if you use the SPI hardware board, so the control refresh rate is like, I think it's something like 50 microseconds. But it's a very lightweight implementation. If you use the Linux embedded system, it will be more. It's really so I wouldn't say there is much of improvement compared to what exists. Especially like Beta, I think is very good on this. Yeah, it's more on the audio latency.
Okay, thank you. And we have more time for the discussion about Linux Audio Conference 2026.
Thank you.
So thank you to the speakers. Thanks to Victor for chairing the session. So we have about 15 minutes, which is kind of short, to maybe have an open discussion on, I think people told me about like 2 potential topics. The first one is potential organizers for next year's LAC, because like so many of you are here, like so it's probably a good time to maybe talk about this. Like LAC was. Well, I wouldn't say dead, but like didn't happen for like 3-4 years, and so now we have a lot of people here. We see there is a dynamic, so it's probably a good time to actually keep that going and make sure that 3 or 4 years gap doesn't happen again. So I think that's maybe one first topic that we can talk about. Another topic which was brought to me like by a few people and that I think we should talk about here as a community is questions about maybe having some form of ethical statement or something like this for the conference in general. So the reason why those people talked to me about that is because I think this year there are a couple of papers where people were like, is this okay to be at LAC or not? I'm not gonna tell you which one, like, but I think or maybe you can guess, and so as far as we're concerned, like we respected the reviewers' decisions, and those papers were actually pretty well ranked, but then it becomes a question of is it acceptable to have papers on things about topics that are potentially not acceptable for some people who are here, including maybe like surveillance, or things like this. And so I think we need to have a conversation about that, and so usually for other conferences there is like a steering committee and there is a board and there is like people making decisions about that kind of stuff. LAC is way more open, and so I think because it's open, it's good to keep it open for like all topics, and not put like rules, but if you think that it's necessary to do that, I think this is a conversation that probably needs to happen now. Okay, so I don't know with which one you want to start, like the easy one or the maybe less easy one. So yeah, Victor.
So I'll start with the less easy one.
Maybe it's better to start with the less easy one. Yeah.
No, the less easy one is the second one, actually.
Oh, you think so? Okay. Yeah, actually.
So in my opinion, that's my personal opinion, we shouldn't, like we can have a statement that's general enough, but we shouldn't be limiting scientific sort of thought and research, and even if it falls in areas that we are not comfortable with, we should just be able to handle that and in a well sort of, in any way we feel like, but we should, and there is space for that. So when we're sort of having the papers and there's space for that, we're not really say, oh no, we present the paper and that's how the final word about it. It's people can say, well, I think it's questionable or whatever. So yeah, that's my opinion. Okay, and I'll move on to the next one, maybe David.
Any other? I agree with you. Like that's my opinion too. But
personally, I also wouldn't say that we should limit those things. But having a statement and like a certain commitment to openness and to open source software and like contextualizing it that way would probably help to sharpen the profile a bit. So like. And I don't think that would be wrong either. Not like to bar people from entering, and like it's interesting probably to everybody here to see that these things are going on and how they connect to the world of Linux audio. So yeah, but again, like having some kind of commitment would sharpen the profile in that sense.
Yeah, very good point. Yeah.
I agree with the previous opinions, but also maybe my two cents that even sound as a technology can be weaponized and can be highly unethical, but it does not mean that we should not talk about that. So maybe technology and knowledge, it's a matter of how you use it, but preventing it from being shared, I don't think, yeah, that's something we should do as a community.
There is another one at the middle after that. Yeah.
Again, I think that we shouldn't be limiting as such. It might be an idea to have an advisory notice that you may hear and see things that you don't personally agree with, but not to actually limit it. It's got to remain open, I think. Otherwise, it's no longer open source, is it?
Agreed.
Also related to both of them, there's a lot of Mac users out there, so maybe you should rebrand it to the Libre audio conference, keeping the L. And then Libre has also the sense of keeping open-minded and having the freedom of presenting anything. So might, well, kill two birds with a stone.
There is someone in the middle who's been trying to say, yeah, thank you, Robin.
I think it's like it's a bit of a minefield, really, and I think there's like a spectrum. There's kind of a balancing act. So on the one hand, like yeah, we'd love to live. All of us would love to be in a space where no one's offended and everything is rosy and unicorns and rainbows, but. On the other end of the spectrum, so I mean, in order to have that though, you need to have like some defined rules, and then the people who define the rules suddenly have power, so it becomes a whole political thing. So which is, on the one hand, maybe if that's your thing, great. I think probably here, also facing issues with like just getting the thing off the ground. It's best to avoid that. I think probably, avoiding that kind of strict kind of, regulatory framework would be much better. And I think at the end of the day, everybody's here is an adult, and there's a door over there if anybody's particularly, concerned about things. And I think, really, if anything's massively egregious, then I'm sure nobody would be concerned about, saying no, like, or if someone wants to present a paper about the murder bots that identify, the people that we know we don't really want using the sound of their voice. I think probably, yeah, most people will be okay with excluding a paper like that. But having some defined framework, I think maybe would not be the wisest thing. Yes.
Agreed. Nando? Yeah.
Yeah, I second Robin's assessment, because I see in some isolated cases, obviously, a disconnect between the name of the conference and some of the submissions. So it's not about limiting scientific research or imposing controls, but we are so far, the Linux audio conference. So if a submission is not using Linux in any way, I don't think it belongs here. It's the same as if, I don't know what example to say, but if you have a paper on food distribution and you submit it to a conference about engineering, it's not going to be accepted. And that's not necessarily about limiting. So we can either, from my point of view only, right, either introduce this artificial limitation, but it's predicated on what the conference is about, right? Or open the conference to other systems that are maybe developed on non-free platforms, but that are free themselves, right? If there is something that's proprietary all the way through, I would say it doesn't belong here. But that's just my opinion. So I see this conflict between what we're supposed to be about and some of the submissions. but I'm close-minded, I think.
I would agree with Nando about this. I think the criteria should be, is it open source, is it audio? And if it's either of them, okay, accept. Regarding things that we may not like surveillance or even military applications, not talking about them, keeping silent about them, won't make them go away. So I think it's better to accept such things, so we are at least aware of what's happening. And if it's interesting in a technical sense, why not?
Yeah, I agree. And I would say to both of these contested topics, I think like dropping papers because they are about things that we might have questions about is only even conceivable to me if there's a resource limitation. Like if we have too many papers and we get like 10 papers on audio forensics, then we might say, hey, maybe this is better off at an AES conference on audio forensics or on surveillance. So then let's talk about it, but let's not limit the scope of what we can think about and learn about when it's not really needed, because we're not like being unable to do other things at the same time. And about platforms, and I mean everybody who's working with software professionally will have to operate other less happy operating systems, and we all do that, and that's fine. For me, I think the cutoff is it accessible? Like, for example, if somebody delivers a great open source initiative that would require me, as in the example for automotive FPGA, to fork out a license for 15K or something, then it's not interesting to me because it's inaccessible. Or if something only works on Windows, even though if it's open source, it's inaccessible for many people, and then maybe not prioritize it. If it slips through, it's fine with me. For me, it's important that whatever we do is accessible to as many people as possible. And I think it's a bit of a, we shouldn't have a rigid structure. We should have like a guideline, some sort of spirit that the conference is about, and then just apply that in a very generous way. And I'm also very open to dropping the Linux audio conference, because it was cool when we started it, because that was the epitome of freedom. And now we have open source projects that are inherently cross-platform and that enable us to get people into the open source spirit in a much easier way. So when I work with students, they are not, the first thing they do is they're not going to install Linux, obviously. The first thing is they're going to install a tool chain on a proprietary system of their choice, and then they gradually go, hey, it's cool to own my means of production. And that is, for me, the priority of this conference. And if it means changing the name, I'm all for it.
Benjamin, I think Jonathan was waiting for a while, so then,
yeah. Regarding the fact that we should accept every paper that is academically correct and on the superficial part, and ethical part less so, but at least if there is a contradiction in a debate about it, and if people that disagree with the contents say it loudly, like, no, surveillance is not okay with me, you give a platform to this paper, but I don't see many people saying out loud, no, I don't agree with what research you are doing. I think that giving a platform to this also lead to silence from the people who are witnessing it. And a few people will be willing to say, no, I really disagree with it, and be vocal about it. I'm saying this because right now it's hard for me to say in front of you, I really disagree with what is doing in this research. I know it exists. It's a reality. I know people are working on it, but I'm against it. I don't want it. It's a support for fascism. I don't want this in this conference. I hesitated to come here today because there was this it gives an image of your conference. If you host this, and if you accept this kind of publications, it sends a message to me that is clear, that is okay for, not clear, but I don't know what you people think about this. And I'm coming into a community and I don't know what this community thinks about this. And I don't know if I can express myself freely, because people who are doing this are not my friends, really not. So okay, so if you accept this, also you need to let people say they're not okay with it, and I'm not sure it's going to happen. So.
So, thanks for the opinion. But one thing that I think about the name change discussion. On the one hand, I'm a little bit on the fence about it, because, I mean, I'm by no means a Linux audio veteran, but I feel like it has changed a lot, no, from 2000 something, where Linux audio was still like kind of uncharted territory, and today there's many ways to use Linux for making music, and that's where I'm coming from. And on the one hand, I totally agree that including people using open source software on other platforms is a good entry point. But on the other hand, I realized coming here how much of a Linux musician I am, how much my art practice and my music practice and my development practice is rooted in the system and in the workflows of the system and the affordances that only this system gives me, in a way. And so in that sense, to have a space that is explicitly a space for people who exploit this system for making music, for making sound, for making audio, also would feel like a great thing. So, and then just not having that and having a plain Libre, or a Libre audio conference, there would still be a space for Linux musician, but having explicitly would also be a nice thing. So I just wanted to...
It doesn't change the acronym too, which is good.
Yes, it doesn't change the acronym, but yeah, just something I wanted to contribute to the discussion.
I'd like to take it to even a lower level. The Linux Audio Conference used to be organized by linuxaudio.org, a consortium. Robin was part of that, and Iko Bukvic, and Dave Phillips, who left us a couple of years ago. But that consortium has become a bit of a very loose organization. And so I hereby like to take this advantage of all you people. If anyone is interested in, you were talking about a steering committee or an advisory board. It doesn't really exist at the moment. You took your own, how to say it in English?
Yeah, and I feel like that's kind of how LAC has always been working anyway. And, like, I mean, so there are some limitations to this, like as we see now. But it's also good that remains like very open and very like.
That's very true. That's very true. Yeah. But it could be an option that there are some people who are still loosely organized and talking to each other throughout the year or through or in advance to any future LAC. And I would really happily welcome anyone who would be interested in that to, because at the moment I'm the only one maintaining linuxaudio.org, the server and the wiki and everything. And the board is now basically only me, which is not that bad, but because, like you said, you fully organize this yourself. So, but maybe there are people organized in, like discussing outside of the conference things about organizing stuff or thinking about what we have discussed here just recently. So maybe that's see it as an invitation, and maybe we could talk about it. Yeah, like I said. That's it, actually. Thank you. Fernando. Sven.
And we don't have much time left. I'm gonna be a pain in the ass with this. I'm sorry, but we really need to be on time at the canteen because they're not as libre and open as we are. So.
Okay, then I will try to make it short. I just want to, on an ethical point of view, I'm with you totally. I don't like fascism either, and yeah. But as I am a research assistant in a cybersecurity campus, this talk was one of the only talks that I could recommend to my students studying digital forensics and get them hooked on the whole open source and Linux ecosystem and something like that. So from an educational point of view, I think to be more open would be good.
Thank you. So maybe we can have another little talk like this, like before the end of the conference. You know, like I think it's good that we do this. Actually, this is I think that's important. So we're gonna have to stop now, and I'm really sorry about that. But I'm really worried that people don't eat. So I think we can take a break. And if one of you is like, I really want to organize the Libre audio conference next year. Yeah, like, you know, start thinking about it. Like, we'll have another discussion about that. Thank you.